All right, good evening, everybody. Thank you for joining us. We have a great meeting planned out tonight. We have some crazy devoted members who are going to come speak to you tonight. We have lots of different subjects. So we're going to start off with our usual Ottawa skies and our astronomy news. We've got some pretty exciting updates this month, I'm sure you've heard. And then we're going to have Hugo Lama, who's going to speak about ancient celestial sky charts. And after the break, we're going to have Doug George, who's going to come present on different kinds of chips. So we have 5 new members in the last month. We have Michelle Bois, Gary Brooks, Brent Cunningham, Tom Harris, and James Lane. Let's give them a warm welcome. So we've got some members in the news. We've got quite a few this month. So first of all, this isn't necessarily news, but we're going to make it news. I believe a member of ours, Stephen Papa, for 7 years this man has been fundraising to build an observatory in the Pontiac. And so this week, just a few days ago actually, he finally reached his goal of $55,000. So congratulations to you. And so next up, this is a spread from Sky News. You might have seen that recently. The first picture in the top right was, I believe, was taken by Howard Simcover, who is a very long-time member of the Ottawa Centre. Next is Mark Narwa, who is not a member of the Ottawa RASC, but he is an Ottawa citizen, and we thought it was worth mentioning. He recently donated a 4.5-inch reflector scope to the Ottawa Public Library. This was actually last summer, and the RASC attended a special launch event, and I believe it was Mike Muggenham who gave a speech on behalf of the Ottawa RASC. And finally, this has nothing to do with astronomy. But we thought it was worth noting our member again, Howard Simcover, who was on the cover of the Ottawa Sun for his work with G.A. Snyder, the photographer. And so next up, we'll jump right into Ottawa skies, so I'll hand the mic over to Dave.
Well, good evening, everyone. Let's take a look at what's happening in the Ottawa skies this month. First of all, the moon phases. We have a full moon on March the 12th, and we also switch to daylight savings time, unfortunately. It means we don't get as much time for observing. I guess we do, we just have to shift the time to a later time. In terms of the planets, Mercury is not visible this month, but since our next meeting occurs before April the 1st, we have the greatest eastern elongation of Mercury, and look for it in the evening sky at sunset on April the 1st. Venus is visible in the evening sky, and Mars is also visible in the early evening all month. Jupiter is visible all month. It's coming into a reasonable time frame for observing, so 9:16 and then 8:01 towards the end of the month on the rise times. Saturn is visible in the early morning. Uranus is visible all month in the early evening, and Neptune is visible in the first part of the month in the early evening. Iridium flare best view. This is based on data with somebody standing at the corner of Kent Street and Nepean Street. This is where the software that I use, Heavens Above, thinks Ottawa is. So at this particular point, nice bright flare on the March the 29th at 7:31 in the evening. Next month, I'm going to show you how to determine the best view from your location. I'll walk you through the steps that I go through for this. The International Space Station, the best viewing date is March the 30th, and it's around 8:12 in the evening. Again, the International Space Station goes across many times. By the best viewing, I try to pick one that's highest in the sky and is up there the longest, and that's how I pick that date. There's a picture of its path across the sky. And there is your cartoon of the month. Thank you very much.
All right, so next up we've got Al Scott with his astronomy news update.
Good evening, everybody. So, the news for this month. What should I say? Anybody at all hear about the NASA press release? A few people? Okay. So Kelly tells me that I've got more than 10 minutes to talk this evening, so thank you. I'd like to discuss the discovery and announcement regarding TRAPPIST-1 system. So TRAPPIST, does anybody know what TRAPPIST stands for? TRAPPIST stands for Transiting Planets and Planetesimal Small Telescope. And you can see it's actually a pair of small telescopes. TRAPPIST is devoted to the detection and characterization of exoplanets and the study of comets and other small bodies in our solar system. Exoplanets, of course, being planets around other stars than our own. TRAPPIST consists of two 60-centimeter robotic telescopes, one located in Chile and one in Morocco. So this discovery was made by a type of telescope not far beyond the reach of some amateurs. And the University of Liège is one of the leading authors in this study. Now TRAPPIST-1, what do we know about it? What is the discovery? TRAPPIST-1 is a planetary system located 12 parsecs away from the solar system, about 39 light years. From Earth, it's located near the ecliptic in the constellation of Aquarius, around a star, TRAPPIST, which is 12 times less massive than the Sun, and only slightly larger than the planet Jupiter, although it's about 84 times more massive than Jupiter. There are at least 7 planets in orbit around the star, and the entire system is actually similar in size to Jupiter and its Galilean moons. At 2550 degrees Kelvin, the star is termed an ultra-cool red dwarf star, and it has an apparent visual magnitude of 18.8, so don't go looking for it with your eyes. This is something you do need about a 60-centimeter telescope to see very well. Metallicity of the star, in other words, the content of heavier elements than hydrogen, is consistent with our solar system. So it has a lot of heavy elements there that obviously have formed planets. So it's an evolved, older, younger system, not a first-generation star. In contrast to our much larger primary, which was expected to burn out in around 10 billion years, TRAPPIST-1 could be an active main sequence star for up to 12 trillion years. So imagine having a civilization on one of these planets. You could be there for a long time if you wanted to. All the planets in the Transit-1 system are interesting and easily discovered because they transit the star. In other words, they go between us and the star and they cause a slight dimming that you can measure using a CCD camera behind your telescope. Using the transit signals, astronomers measured the orbital periods of the planets and saw repetitions in these dimmings. And there were 7 different periods that they were able to pull out. And from this, the timing of the transits, they can calculate the sizes of the planets relative to the size of the star, which is known very well from models of stellar evolution and brightness measurements and temperature measurements that can be made by telescopes. Combining this data with radial velocity measurements of the star, you can actually get estimates of the mass of each of the planets. And based on the mass and the size, you know their density, and so you can tell whether they're rocky or gas, because there's a big difference in the two densities. And so what we know is that all 7 of these transiting planets are roughly close to the size of Mars, the Earth, and Venus, and rocky in composition, and potentially having lots of volatiles, like water. The planets were found in May of 2016. The first 3 planets were found by the TRAPPIST telescope in May of 2016. Because we know the distance of the planets to their star and the temperature of the star, which we can measure from its color, we can deduce that they receive an amount of light similar to many of the planets in our solar system, from Mercury to just beyond Mars. And in fact, what that means is it's very likely that liquid water could exist on the surface of many of these planets. Since the initial three-planet discovery, several other telescopes have been intensively studying the system. NASA's Spitzer telescope, for example, and they've discovered up 4 additional planets during the study. So there's 7 total planets that have been discovered now. 3 of them being in the habitable zone. So I think actually the 3 that are in the habitable zone kind of goes from here to about here. So these 2 are kind of firmly in it. This one's on the cold end, this one's on the hot end. This is the most biggest number of rocky planets and the greatest number of potentially habitable worlds ever discovered up to the present. So here's a comparison graphic between our Sun and TRAPPIST-1. The TRAPPIST telescopes have been studying these small red dwarfs because it's easier to see the planets around them by dimming, because planets dim a larger percentage of the star's light around such a small star. And typically they orbit in closer, and they orbit much faster because they're in closer. So it's easier to verify the planet's orbits this way. As is typical for these ultra-cool dwarf stars, TRAPPIST-1 has a high X-ray luminosity, similar in brightness to the Sun in X-rays, despite its much lower visible brightness. What this means is that the close-in planets, much closer to the star than Mercury, they're actually the same distance as the Galilean moons are to Jupiter, are bathed in X-rays and extended ultraviolet radiation. So before you decide to build a rocket to go vacation there, you should make sure to bring some sunscreen. As well as that, let's think about the discussion about habitability. I mean, this is what people are interested in. Is this something where potentially life could exist? Is this something where people could one day go, despite the distance, and survive? So the questions are is there air, is there water still on these planets? And what do we understand about the evolution of planets from a planetary nebula that could help us in this decision? Well, the X-ray flux, for example, we know planets that are bathed in a lot of solar wind, the X-rays and solar wind will carry off the atmosphere of the planets. It'll strip it away. Especially for these ones, a lot of people think that close-in planets to these ultra-cool stars, these mega flare stars, may have their atmospheres completely stripped away. And if that happens, then any water on them would quickly evaporate, be ionized, the hydrogen would leave, and perhaps there'd be a reservoir of ice in a polar cap, or maybe an opposite sun cap. But they may not even have an atmosphere. If these planets formed as close to their primary as their current orbits imply, it's likely that they would have formed in a relatively hot, dry area of the solar nebula, the planetary nebula, where there weren't many volatiles. Typically, the ice and water exist further out, and the gases, because in close to the planet, is mainly just dust that exists to coalesce into planets. So if they formed in their current orbits, it implies they probably don't have much water to begin with. Also, because of their closeness to the parent star, tidal forces on the planets will be much higher than would have been experienced on the early Earth, for example. So these planets would undergo significant tidal heating in their orbits, and it actually will eventually tidally lock them to the star, so that one side always faces the star. There's always a hot side and a cold side, and they orbit such that the day length is the same as their year length. And this tidal heating could cause global volcanism. It might drive off any water that they started with, and they could risk being permanently desiccated deserts on one side and permanently cold on the other. But, okay, this didn't come through. I'll go back to the other one. There was a little video there that I wanted to show. On the other hand, there is a possibility that things aren't so bleak for this system. Significant heating of the core of the planets could enable the planets to maintain a strong dynamo. They could have strong magnetic fields that would protect their atmosphere from the solar wind, like the Earth's does. And astronomers are studying these things, modeling them, trying to figure out whether or not they may still have an atmosphere. They've also noticed that the orbits are very tight, and they're in resonances. What that means is that when one orbits twice, another one orbits 3 times in the same period. So they're in these gravitationally locked resonances. And what this suggests is that they may have formed further out in these resonances and then migrated in through the primordial nebula. So they may have formed in areas where there was more ice and more water in the nebula and then migrated in. In fact, models suggest that planets can't form in these tight orbits on their own in the same place, because they would scatter and they would encounter each other and fly away. To get in such a stable, tight system, they basically would have to form further out in these resonances. The resonances stabilize the orbits, and as they go through collecting gas and dust from the nebula, they spiral in, maintaining these resonances to keep them in stable orbits. So it's very possible that they actually have formed where there was a lot of volatiles and ice, and some of them could have started out as ocean worlds. And if they've been able to hold on to their atmospheres through the early life of this star, then perhaps they still have atmospheres and oceans. And we're not really sure at this point. Ongoing studies from more powerful telescopes will seek to detect signatures of water and oxygen in the atmospheres of these planets as they transit their primary, looking for ozone and other signs of life, signals that perhaps living chemical processes are ongoing, non-equilibrium chemistry. The age of TRAPPIST-1 is uncertain. Because these stars are very active when they're young, once they calm down, TRAPPIST-1 is relatively quiescent. They don't see mega flares in this. People have been looking at it, they haven't seen flares, so they think that it's older than 500 million years, but less than 12 trillion years, because obviously that would be older than the universe. But they don't know, because once these things reach their main sequence, they don't change much over thousands of billions of years. So this could be a very old system. After millions of years, all the planets, as we said, are probably tidally locked to their primary. So this is an interesting scenario. What would the weather patterns be like on a planet where you have an ocean and one side of the planet is always facing the star? Well, people have been using climate models to try and estimate. Computer models are trying to figure out what the wind patterns would be like. Would you have raging global winds? Would you have circling winds? And it seems to depend on how fast they orbit the planet and how much angular momentum the planets have to determine whether or not they have a fixed wind pattern or whether they would have jet streams like on Earth, for example. And it's likely that these planets do have jet streams which take the warm air from one side and put it around the other side, so that the cold side isn't all that cold, and the atmosphere, if there is an ocean, will have clouds, and the clouds will tend to insulate the cold side. So you'll actually have a very broad, what you would call a very broad area where the temperature would be quite moderate around the terminator. So you'd have kind of a twilight zone, if you will, where the sun is constantly setting at the same altitude, where the weather might be quite nice. And in fact, people are thinking, what would it be like directly under these things? Well, models show that because of the upwelling, all of the heat, the upwelling convection would create huge thunder clouds at the subsolar point, which would actually shade that area and cool it. And it may even protect from ultraviolet rays and extreme radiation. So there may be quite an interesting weather pattern on these planets. So we don't really know. There's a lot of discussion amongst scientists as to what these things might be like and whether or not life could exist. We'll keep our fingers crossed and keep listening for more information as the science progresses and as people do more studying. The orbital periods of the planets in the habitable zone in this system range from 4 days to 9.2 days. So the year and the day are 4 Earth days to 9.2 days long. And because they're so close together, they actually would appear, their neighbors would appear in the sky about the same size as the full moon does on Earth. So you'd see all these very large bodies at different phases. You'd have 5 or 6 different very large crescents in your sky if you were on one of these planets. So it would be quite scenic if nothing else. Unfortunately, SETI has not detected any radio emissions from advanced TRAPPIST-1 civilizations, so we'll have to wait for that. Any communications, of course, would have a 39-year delay, so we wouldn't be able to transmit back and forth even if there were. But stay tuned. A lot more, I think, will come as the bigger telescopes continue to study these things, and it's a very good target for looking for water and signs of life, and I'm sure we'll hear more in coming years. So thank you.
Hey, thank you, Al. That's really exciting. So without further ado, let's welcome Hugo Lama.
Okay, now you heard some of the latest things that are been happening. Now I'm going to take it back to about 1700 BC. Anyway, the reason I'm up here is you may have noticed there's a couple of star charts framed down below here that I brought in. I got these in one of the draws. These came from on one of our draws, and I looked at them at home and tried to figure out what they were, and it's a little confusing. So I thought, well, I'd better investigate and see what this is all about. They're very nice, high-quality charts. And what I discovered is, in my investigation, these are charts produced by Andreas Cellarius, and they came from a famous Harmonia Macrocosmica atlas that was put out way back in 1660. Now, in the first part, he goes through all three of the major theories of covering 1,500 years of astronomical theory, from Ptolemy, Copernicus to Tycho. But then the rest of it is full of star charts using the mythological figures and the Christian constellations. And so these charts, one of which is a copy here that I brought in, it's got the northern hemisphere and the southern hemisphere. This is the northern hemisphere. These charts were part of that huge volume. And so you look at that and you say, okay, well, what's what? You try to identify the constellations, and you say, oh yeah, there's the Bear and on. Okay, so there should be the Dipper in there. But then when you look closer and try and identify some of the others, you kind of get lost. And then I realized, well, wait a minute, something's not quite right here. And what it is, it's a mirror image. So here I flipped it, and I've identified in yellow, and you can see the Dipper there on the Bear, and you can see a W there for Cassiopeia, and down below there's Orion, again in yellow dots more or less. Now to confuse the picture, this is on top of a drawing of the map of Europe. So it's even more confusing. So you have these mythological figures and drawing, and it's a mirror image, and the stars are not that clear. So how do you make any sense of this? So my curiosity was aroused. Okay, why in the world did they make mirror images? It doesn't seem to make much sense. I can see the mythology, okay, but why the mirror image? So I looked into it further, and I'd like to share with you this evening what I found out. Now, okay, this is the same thing in more modern design, where you have lines connecting the different stars. Now, what I found was, if you go way back in history, for instance, this is a copy, a Roman copy of a Greek statue, and you see Atlas holding the celestial sphere. And on that celestial sphere are the constellations. So you're looking down on that globe. Now, in order to see those stars as we see them, you'd have to be inside that globe. Well, I guess they didn't have planetariums, so you'd have to have a very huge ball to do that. Anyway, so as it says here, the Earth's representation of the sky were actually globes on which the constellations were shown as though viewed from a godlike position beyond the stars. hence my title of my talk. Now, from that, later on, they developed the astrolabes, which were flat pieces, usually on brass and such, with inscribed lines, and also with the stars. So it's a flat projection, which, essentially doing the same kind of thing. But if you go back even further to see what's happening, in this case, here's an example of a Babylonian cylinder seal. And this depicts Hercules, or known as the kneeler back then. And you can see from that image on the left that it looks very much like the matchstick drawn one on the right there. You can really correlate them, which is not the case with most of the other constellations as we know. But like, 1700 BC, that's going back pretty far. Now, mind you, in order to produce that seal, the artist would have had to make a mirror image of that to make it come out correct, right? Now, going further, we go now to the other side of the globe, and in China, back in about 650 AD, there's a famous star atlas showing constellations. And in this case, they actually show lines connecting the dots as opposed to mythological figures. But in their case, they had up to 260 constellations, counting more faint stars than we do, up to like over 1,300 stars. And the constellations were much smaller. But they did not correlate these with mythological figures, but according to my information, they related more to the emperor and his entourage and different things, his bath and things like this. Now from that, and then this appears to be in the correct, not mirrored, but the only thing we can kind of make out, I would say, is probably just the dipper here. The rest are, you'd have to study them more carefully. Now, over in the Western world, they didn't start connecting the stars with sticks or with lines, straight lines, until about 1786. So that's quite a gap. And one of the most well-known was Alex Ruel, who started doing that. However, the Arabs were very good observers of the skies. And again, a very famous atlas was a Book of Fixed Stars by Al-Sufi in 1000 AD. And he did all the, he did all the constellations, more or less as we know them. But you'll notice he has both. He has the mirrored image and the image as we see in the sky, where I've indicated with the red dots so you can identify Orion there. Now, further, we go to the other side of the world, to South America. Up in the Andes, apparently there are these Inca astronomical water mirrors, which they use to help sight against their rocks where the sun is rising and the moon is going and so on and so forth, and presumably some of the brighter stars. I don't know how well this works, because if there's any wind or something, it's going to be all wobbly and won't get a very good image. But apparently that's what it is. And again, another example. Question is, it's a bit of a mythology. Is it really an astronomical mirror, or is it a grinding bowl? Now, I don't know, maybe it helps those people that draw stars, maybe it helps correlate the image if you're looking in a mirror there and it's on a flat surface as opposed to look up in the sky. Now, still in the Andes. Okay, here we see the Southern Cross, and there's the coal sack and the Milky Way there. I'm not familiar myself with that part of the sky. However, the Incas had both bright star constellations and dark star constellations. They assigned names to the dark parts of the Milky Way. So for instance, there's the llama there, and the two eyes are the Alpha and Beta Centauri, and then the coal sack up there is partridge, and then there's clearly a serpent there. However, you will notice, if you look at the real sky, okay, you can see the two eyes of the llama there, okay, but, and the coal sack is there, but the serpent is pretty well not visible. Now, mind you, I presume up in the Andes they had very clear skies. In any case, they had light constellations and dark constellations. Maybe they knew something about dark matter. Okay, now what surprised me, there's also, when I look on the internet, there's also some people looking for mirror images star charts in the modern day. And I wonder, why in the world would they want to do that? But it makes sense. If you're doing star hopping, you look at a particular brighter star and you want to hop over to the next one. If you're using a refractor, okay, well, you don't want to lie on your back to look at the stars in the zenith, so you put in a little mirror here, a little diagonal, so you can look at right angles to it, or a prism. Well, as soon as you put a mirror in, of course you've got a mirror image, right? Now, not only that, with a normal astronomical telescope, your image is upside down. So here you've got mirror image upside down. But you'll notice the finder scope doesn't have a diagonal here. So there you're looking through just upside down. And then when you look at the sky, everything's correct. So now you're trying to use this system to try and navigate your way around from one little star to another star. And I think you can see that you run into some difficulties. Now, in the modern age, you've got a solution. You've got iPads, you've got laptops, you display your star chart, and you flip them with your software. Okay? But I also discovered that there is a well-known Ruckel's mirror image of the moon with up to 300 named craters. Perhaps Brian is familiar with this. Then you can do your hop from crater to crater without getting lost. And finally, for those not serious, well, even serious astronomers, if you're not quite sure what's what, you can get an iPhone nowadays. You can point it up at the star or what you see, a bright object, and it tells you, oh, that's Jupiter, and you see the satellites and everything. You stare at that for a little while, and you say, oh, great. Then you put it down, and you can't see a thing, because the iPhone has blinded you, and your night vision is totally gone. Thank you. You will be able to get these two charts after our program tonight. So I would recommend that, particularly to anyone who's a teacher or someone who's dealing with public. Sitting down in some gloomy basement might not be the best place for them. And they are worth something. I looked on Amazon and they are actually selling these things.
All right, so before we jump into our break, we're just going to go through a few membership benefits. We've had a lot of questions about this lately. And so if you do choose to become a member of the RASC, of course, there's the monthly meetings, which are open to the public. However, we do have special subscriptions to Astronauts, which is our monthly newsletter, Sky News, the RASC National Journal. If you're a member, you also get access to the StanMod book library, as well as the Ted Bean Telescope library. And so we get a lot of questions about this. So as for the book library, people don't know where to find it. So how it works, you can just come down here during the break or after the meeting. We keep all the books right behind the stage here. And so Estelle is always here if you have any questions. If you'd like to get a book, she will be more than happy to help you. As for the Ted Bean Loan Library, I believe Al is in charge of that?
Yep.
Okay. So if you recognize Al, if you don't, just come see me and I'll get you hooked up. Well, we have a few telescopes that you can rent out either for a month or for 6 months. You can rent it out for the year. And if you don't know how to use it, I'll find someone who can help you. Finally, you also get access to SmartScope, which is an ongoing project, and to the Fred Lossing Observatory. The site and the actual telescope, I believe, requires a bit of a lesson, and it's an extra fee of $35. And as you can see, you get many, many more benefits. So I believe, Chris, are you going to change it?
Yeah, I'm going to do
Okay.
it. Go ahead.
Okay, so I believe Carmen Rush is going to come speak to the volunteers.
Hi, everybody. Well, last month, if you remember, that was showing, and I gave a very impassioned plea for some volunteers to step forward and help us out with some of the roles that we're still looking to fill. So, Chris, next slide. And we're down to only 2 left. So I'm going to give another impassioned speech about the fact that I've been in the club for, I don't even want to say how long, but I will, since 1984. And I was kind of reluctant to really get involved. I was very much sitting in the wings, and it took a few people to come forward and encourage me to get more involved, and just that little bit of encouragement really opened a whole new world to me for the club, because if you volunteer for something, it really gives you a better chance to meet people and talk to people and just understand what the club is all about, and you just feel more involved, and it has much more meaning. At least it did for me, and anybody else who's volunteered, they would tell you the same thing. So if somebody's out there who would like to help on with flow. We do have a good team assembled, but nobody really feels comfortable being the lead person. Now, the lead person actually can be a good job because you delegate. So you can have lots of ideas and pool those ideas and then, get the crew going. So it sounds bad, but frankly, being the king is probably the best thing to be. So if anybody's out there and wants to still be part of the flow team, that's the Fred Lossing Observatory. We're in the middle of planning some rather big renovations to improve the site and improve the building and house some more telescopes to make it more appealing to more people. So that's certainly in the works, but we just need that one extra person who has some leadership strengths. And the other one is Light Pollution Abatement Coordinator. So, for example, if you would speak to Rob Dick, he would give me more information about what he was up to in these last years. That's more in charge of trying to encourage, if there's a new building site going up, try to encourage either the city or the builder to use more friendly lighting, not just beaming it up to the sky, which a lot of places like Walmart and so tend to do. It would save the company money, it would save the city money, so that would be more of an kind of like an overseer person to be aware of what's going on in the city and then maybe approaching the correct people that are in charge of the building site to encourage them to be more energy efficient, but also good for us, better for astronomy. So if you think you might be the person for these 2 jobs, please speak to Tim Cole or anybody else who looks official in the club afterwards. And if they don't know if that's the right job or if they can't give you more details, they will certainly bring you to Tim Cole. You can even speak to me, and I will bring you to Tim Cole. And that's it for me.
Thank you, Carmen. All right. Okay. So you may have noticed that we somehow misplaced the tickets, the door prize tickets. So if that's okay with everyone, what we did is we wrote some random dates down. And I'll call them out at the end of the meeting, and if that date happens to be your birthday, then you can come get a door prize. We also just wanted to mention that the 2 star charts that are in the door prizes should go as a pair. So whoever takes one should take both. So we're going to move right on. Please give a warm welcome to Doug George.
Hi. So some of you probably know that I run a little company called Diffraction Limited, and over the last couple of years we've actually been also making the SPIG CCD cameras. So I have quite a bit of insight into the imaging technology. And people have been noticing lately that there's these other kind of sensors called CMOS sensors. And there's a lot of confusion about what's better, CCD or CMOS sensors, and why. So I thought I'd just give a little introduction to the technology and explain what the heck are the differences. Let's see, oops, wrong way. Okay, so here's the key thing. So a CCD sensor is made of silicon. It works based on the full electric effect and has an array of pixels. On the other hand, a CMOS sensor is made of silicon, works based on the full electric effect, and has an array of pixels. So that obviously we need to dig a little deeper to see what really the differences are between these 2 technologies. So I'm going to get into a little bit of detail in technology and physics here, but no math. So this is how a light is detected in a camera, and it's based on something that was first explained by Einstein, and is actually what Einstein got his Nobel Prize for. He didn't get his Nobel Prize for relativity, he got it for the photoelectric effect, which is quantum mechanics, which is funny because Einstein never liked quantum mechanics. In any case, basically the simple idea is that a light comes in, hits a piece of metal, and knocks off an electron, and that flies away, and then you can detect that. And that's how they used to do things back in the day of electron tubes. We don't use that kind of technology anymore, we use semiconductors. So what we have here is a crystal of silicon, and we use ultra-pure silicon to detect light. And it's also what's called a semiconductor. Sometimes silicon can be a conductor, and other times it can be an insulator. Actually, in its default state, it's an insulator. And the light can actually penetrate into the silicon. It doesn't just hit the surface. So unlike in a metal, the photoelectric effect happens inside the material rather than right at the surface. So I'm going to talk a little bit about the technology of semiconductors here. And there are basically 2 types of silicon that are used in any kind of electronic device. There's the N-type and the P-type. So what they do is they add a little bit of contamination to this ultra-pure array of silicon atoms, and they use a different atom which has a different number of electrons that circle it. And if you put an atom in there which has an extra electron compared to silicon, you suddenly have an extra electron that's floating around in the crystal lattice and is free to move. And if you put in one that has one too few electrons, you get what they call a hole. And this hole can actually bounce around from atom to atom and also can conduct electricity. So basically that's why silicon is a semiconductor. You can just, with a very slight tweak, you can make it conduct electricity. But so now you've got a piece of silicon sand that can conduct electricity. What's the big deal? Well, you can put 2 of them together. You put a P-type and an N-type together, mate them up together really intimately, and what happens is the electrons in the holes cancel out, and it becomes an insulator again. But it's an insulator that you can overcome by applying an electric field. If you apply it against the N and P going the other way, it neutralizes this area where there's no electrons, and suddenly current starts flowing again. If you put the voltage the other way, it won't flow, and this makes what's called a diode, which only conducts current in one direction, a very fundamental electronic component. And by getting a bit fancier, you can make transistors that are switches that can turn on and off, and all of our modern technology is based on this fundamental principle. Works that way. Now we can add, of course, copper tracks or aluminum tracks to make wires. We can use bulk silicon as an insulator, so we can make everything we need to make an electric circuit. Now, normally, these devices are all sealed up in a plastic or metal can because if light hits the semiconductor, it's going to liberate extra electrons, and that's going to make this transistor turn on all the time. And you don't want that because you want your TV to actually work and not do weird things when you turn it on. So these devices are always sealed up. But you can actually deliberately make a semiconductor device that has a window on it and let the light come in and hit it and do things, make the photoelectric effect, and find a way to read out that image, and you can now display it on a computer screen. So they both detect light the same way, but after that, everything is very different between these two types of sensors. So the first type of solid-state sensor that was ever developed was called the charge-coupled device, and it works basically by having these electrodes that run across the top, and they alternate voltage, positive and negative. And you know that electrons are attracted to positive, so they all shuffle towards the positive electrodes. And so every time a photon of light comes into the chip and hits something and makes an electron, it wanders over towards the positive electrode. Now, there's always a layer of insulation on top, so the electron can't actually get to the electrode and be removed. It just sits there underneath the electrode. And so you leave your shutter open for a period of time, and these photoelectrons start accumulating, and they stay put. They stay in their pixel, which are defined by these electrodes. So that's, so far so good. We now close the shutter, and now we've got to figure out how many electrons are in each one of these pixels. How do we do that? Well, we use what's called a bucket brigade. You'll see that there's a horizontal readout register and a vertical readout register, and they shuffle packets of electrons out to a measuring device. So if you think of buckets collecting rainwater, we could get a picture of the cloud over top. We open the shutter, let the rain fall in the buckets, and then we read them out one at a time over in this corner here by measuring the height of the water in the last bucket. And that's actually how a CCD works. That's why they call it a bucket brigade device. It actually carries a charge from every single pixel, one at a time, into the corner of the chip and measures it using a transistor. So the great thing about this is, although it's a little slow because you have to read them out one at a time, it's always the same measuring stick, the same device used to measure every single pixel. And so it's extremely consistent. And that means you don't get weird problems with noise and strange patterns in the image and things like that. It's extremely consistent, and so you can get a very high quality image, which is what you need, especially when you're going to be doing astronomical imaging where you don't get very much light. You want to preserve every one of those photons that are coming out and measure them very accurately. So this here is, oops, doing it again. Okay, this here is an interline sensor. The pixels are here, and then when it goes to read out, they shift the electrons into these columns and shuffle them down towards the bottom, where they then read them out horizontally, and it goes out to an AD converter and makes numbers that come up on your screen. Disadvantage of CCDs. Well, they're relatively simple devices on their own, but they require fairly complex electronics because there's all these weird, fairly large voltages for all these clocking voltages to make the electrons come out, and they have to operate very quickly, but they're driving large capacitance, so it's hard to make the drivers. And so you end up with a lot of circuitry to make these chips work. It can be quite substantial, the amount of number of power supplies and driver circuits, and then all the fancy low-noise electronics to read everything out, can amount to quite a bit of electronics. So this drives up the cost of the camera. So that is one of the disadvantages of CCD technology. There's been various improvements to the technology over the years. One thing that's very common on what are called front-illuminated devices, the most common devices, is putting little micro lenses. These are microscopic lenses. Now you might realize that a pixel on a CCD chip might be, 3, 4, 5, maybe as large as 20 microns across. That's 20 millionths of a meter, 20 thousandths of a millimeter. So these things are very, very small, and these are itsy-bitsy little lenses. And why they do these is because there always has to be these electrodes on top to control where the photoelectrons go. And so those electrodes are not perfectly transparent. They actually block some of the light. So to make the chip more sensitive, they put these little lenses on that focus the light on the silicon to make it more efficient. And that's one of the various sorts of enhancement they have. There are also some fancier ones which are electron multiplied, where they accelerate the electrons up to huge velocities and then bump them into an atom to make more electrons. So there's lots of different variations on these sensors, and some of them are very, very, very high performance. For example, the backside illuminated CCDs. Now, I said the electrodes are normally on the front. The light comes in through the electrodes, which is a problem. But if you thin the sensor down and flip it over and have the light coming in from the back, there's no electrodes on the front. The light goes right into the silicon directly. And these sensors can have 97, 98% quantum efficiency. That is, every photon of light that hits that chip, it's got a 97% chance of being detected. And that's really good. In fact, it's almost perfect. You really can't make a sensor that's better than this. Just, theoretically you can't. The disadvantage of this technology is making it very, very thin, like 20 microns thin. If you do it a little too much, you have nothing left. If you don't do it enough, it doesn't detect light. So it's a very, very touchy, very stringent process to etch the back of this chip and grind it down to the perfect thin thickness that you need to have it work. So the yield, the number of times you get a wafer of silicon and you put it in the machine and process it and it actually works at the end, is lower than it would be for a standard front illuminated sensor. But the advantage of them is that they're extremely, extremely sensitive. And also by reading them out very carefully and slowly, you can get the read noise down, that's the error in each measurement, down to a couple of electrons. So these are sensors that are almost perfect for all intents and purposes. And this CCD technology is very mature. They've been around for decades now, and they're extremely powerful devices. But, as I did say, a bit complex and expensive to build a camera around. Now, CMOS. CMOS is actually the basis of all our modern electronics. That's basically almost all the electronics, any device you have is now made of CMOS. And it's complementary metal oxide semiconductor. That's right, complementary metal oxide semiconductor. What that means is there's a P-channel MOSFET and an N-channel MOSFET transistor in every cell of the device. And if you put in a high signal here, it turns on this one, and that produces a 0. You put a low signal here, it turns on this one, and that makes a 1. That's a basic inverter device. Takes a 1, gets it a 0, gets a 0, puts it a 1. And you can also make these be amplifiers. You can make them do all kinds of different jobs. So they're widely used in all our modern electronics. Almost every chip in your phone is probably one of these CMOS type devices. Now, let's see about what we could do with this if we make a sensor out of it. Basically, it's really the same, except now you don't have an easy way to clock everything out. Instead, what you have is at every pixel, you have a little transistor that measures the light at that pixel. So every pixel has a light-sensitive area and a transistor, and there's some wiring to read it out. That's good in some ways. It's also bad in other ways because those transistors take up some space. So some of each pixel is reserved for non-light gathering parts, and so that reduces the fill factor, or how efficient the sensor is going to be. But they have other compensating advantages because now you don't have to have all those fancy clocking electrodes and funny voltages and all kinds of fancy readout electronics. Instead, inside the chip, it now actually has its own built-in ADD converter that converts it to digital numbers. And so you plug the chip in and it gives you numbers. It's a complete integrated camera in one chip. So that's a huge advantage, which is why there's so much push to make CMOS sensors work better. And you know how much your camera phones have improved over the last decade. When the first iPhone came out, the camera was kind of, it's okay. Now the cameras are actually amazingly sensitive and quiet, and that's because the economics of making cell phones has really pushed them to improve the CMOS sensors. So the sensors are getting better and better and better. 10 years ago, CMOS sensors sucked. CCD sensors completely blew them away. Now, the performance of those two sensors is actually approaching. So the chips have advantages that they can read out faster usually, much faster in some cases. You can actually take a little piece of the chip and read it out without affecting the rest of the chip. They do lots of cool things. And they're very easy and cheap to run. But, as I mentioned, the readout electronics on each pixel takes some space up, so that reduces how sensitive the camera is. And that really is a big problem for these sensors. Also, because there's less silicon available to collect the electrons, it doesn't take as much light to saturate the chip. Each pixel can only hold so many electrons, and the bigger the pixel, the more light it can hold. But with these pixels that are half full of transistors now, they're actually able to hold less photoelectrons, and the dynamic range, the difference between bright and dark, is more limited. Because every single cell of the chip has its own readout transistor, you have what's called fixed pattern noise. So every single pixel has a different average brightness and a different gain. So the chip's inherently a bit noisier because of that, and you have to do more calibration steps to clean that up. And of course, there's all kinds of extra circuitry in there, which could result in extra leakage, extra noise. So they're typically not as clean and not as sensitive as a CCD sensor. Now, they have made vast improvements recently, but I did say those improvements are done for the cell phone market. So all the chips that are made for cell phones are really tiny. And because they're really tiny, their pixels are really tiny. You're talking like a 1 micron pixel. And that's great for a teeny weeny little lens in your cell phone camera. When you have a telescope with a 2,000 millimeter focal length, that doesn't work so well. Because pixel size is a lot like F ratio. If you have a bigger pixel, it's more sensitive. But these chips have teeny weeny little pixels, and they actually end up having too much sampling and don't cover enough sky if you put them on a telescope. So that's a problem. Now, that's not an intrinsic problem, that's an economic problem. I mean, people have to build new sensors with bigger pixels with the new cell phone camera technology. So, as of today, if you want to get the best possible image, you're going to get a CCD sensor. However, the technology is rapidly improving on the CMOS, and they have huge advantages in terms of cost. So, the economics are going to push CMOS to the fore probably the next 5 to 10 years. And the performance gap is dropping very rapidly. I'll give you an example of how CMOS has been evolving. This is a technology produced by Sony called Exmor. And they start out with a fairly simple, basic CMOS sensor, very conventional one. And then they start doing fancier electronics, like there's a ADD converter on every column of the chip, makes it faster and things like that. And they have double correlated samplers that reduce noise and all these fancy things. And so because they have all the readouts at every column, as you're transferring the data out, there's less noise. It's all digital. So it makes it a cleaner signal. That was the first thing they did. Then they decided to try and make the electrodes smaller and thinner, and so they went from the standard aluminum conductors to copper at 90 nanometers, and then copper at 65 nanometers, and these made their chips smaller, thinner, more compact, and okay. Did we get that back? Thank you. And so this makes it less distance for the light to travel to get to the light-sensitive part, having to go through all this other stuff on the way through, and that improves your sensitivity. So that gave a wider angle of light coming in that you could see because of the shallower pixels, and it also gave them more sensitivity. And then the next generation, they flipped the chip over and did the back illuminated thing that was invented for CCDs. So now, instead of going through the microlens and through this electronics and then into the pixel, they actually go through the microlens and directly to the pixel, and the electronics is behind it. And in fact, they've actually moved now where the transistors are actually underneath the pixel instead of beside it. So now the entire front surface of the chip is sensitive to light again. And it's back illuminated, so there's no electrodes up here, there's no electronics up here, light's going right into the silicon. Basically, you're to the same point now as you were with the back illuminated CCD sensors. The performance should be very, very similar if you do a good job building the chip. So this technology is now in people's cell phones. That's why they're so amazingly sensitive now. And now all we have to do is get them to make bigger chips, so we can have them in sensors that are good for telescopes. So here's a close-up view. Here's a front-loaded sensor with the electrodes and all the electronics in here, and the pixel down here. And here's a back limited with the pixel right behind the micro lens. And again, because all the transistors are now underneath, the whole chip is an imaging sensor, and all the electronics are behind the imaging sensor. So it's a more compact sensor, and there's no wasted space with extra circuitry, and you don't have those transistors taking up space in the pixels. So it's a beautiful technology. And this is a complete camera. You get ones and zeros out of this. You don't get analog signals like the CCD sensors. Now for some bad news. Sony was so enamored with their wonderful new technology for making CMOS that they decided to completely discontinue making CCD sensors. And they make some of the best CCD sensors in the world. Well, they did last year. They don't make them anymore. What they did, though, is they had 2 wafer fabs that were manufacturing CCD sensors. They ran them night and day for a year and made a whole whack of sensors and stuck them in a vault. And us camera manufacturers had to put in our dibs on how many sensors of what type we wanted, and those are all the sensors we'll ever be able to get for the next 5 to 10 years. And once they're gone, they're gone. And this is in advance of them actually coming out with the replacement CMOS sensors that would be of this equivalent performance. So it's not a complete disaster because we have sensors for a while, and hopefully new ones will come out to replace them that are CMOS style. But there could be some other challenges. Many of these sensors are meant for color imaging, so they have this Bayer matrix where there's color filters in the front of pixels. And for scientific imaging, we don't want that. We want monochrome sensors. They do exist. As I mentioned, the pixel sizes are too small for telescopes. And they often have these BGA packages where these balls on the bottom are what solders to the board, all the connections. There's nowhere to put a cold finger to cool the chip down. Because in order to get really good low noise performance so you can run for long exposures, this chip needs to be cold. In a typical SBIG camera, the main sensor is running at -20 to -30 degrees C all the time. Because of the thermoelectric coolers in the camera. This is the other part that makes the cameras big and expensive. But with these type of chip packages, it's very hard to cool the chip. So we also have to get them to make the chips that are going to be more amenable to cooling properly. But there are other companies that are doing some interesting things. Kodak went out of business, but before they went out of business, they spun off their sensor line. They did have, ironically, Kodak invented basically the sensor that put them out of business. I don't know why they did that, but they did. But they spun off the division into a private company called TrueSense, which was subsequently, about 2 years ago, bought by ON Semiconductor, a really big company, which has about 10 lines of different imaging sensors that they've acquired from different companies or built in-house. And they basically took all the people from all those different companies and put them in the same room and said, here, cross-fertilize each other. And so their engineers are busy talking, oh, I got this neat technology, no, I have this other better one, and oh wait, we put that together with this one, and they're making really cool, interesting new sensors. They are still making CCDs though, fortunately. Because some of the big CCDs we sell are actually, the chip is like this large. That's how big the sensitive area of the chip is. And you need that for large telescopes. You're not going to get this anytime soon in CMOS, but they're still making them. In fact, they're introducing new chips. So they recently introduced the KS16200. It's a 16 megapixel chip in the same sort of format as the very popular 8300, which is a very popular 8 megapixel chip. And that's been a very big seller. So that's actually, looks like they're not only continuing to improve their CCD sensors, but they're also making some big moves in CMOS, and we'll see what they come up with. In the meantime, Sony's making some promises about the future, what they're going to do. We'll see how that develops. And there are other companies. E2V, which makes some very high-performance scientific-grade back-limited CCD sensors, is now also making very high-performance back-limited CMOS sensors. These are very, very expensive sensors, though. But for some applications, they are unmatched. And then there's some new entrants in the market. G-Sense is making their G-Pixel sensors, and the G-Sense 400 backside illuminated is one of the newest products. It's a 2K by 2K sensor, 1.2 electrons read at noise, so really quiet. They designed it so you can put a cooling finger on it. It's got low dark current, and unfortunately, although it's got a good sized pixel, 11 microns, that's pretty good for astronomy, it's got a 12-bit ADD converter. Yeah, So, but clearly this is really close. This is really close to being a really excellent sensor. It would probably be worthwhile for some applications to sell a camera with a sensor in it. But I'm going to assume that G-Sense is going to continue improving their chips. And we're going to see more exciting things from them. So I think the future looks bright. It's going to be a gradual transition. Over the next 10 years or so, we're going to see CMOS basically taking over, supplanting the CCD sensors in more and more market segments. But it's going to take them some time before they supplant the highest performance or the largest CCD sensors. So we're still going to see a mix. It's just that CCD is going to have a smaller and smaller niche over time until eventually the CMOS takes over. And this is actually a good thing on many levels. It will make making the cameras less complex and less expensive. It also ensures that the technology will move forward because CCD sensors are actually built using obsolete technology, NMOS or PMOS. And they have to use old wafer fabs to make them. Literally have to use old equipment because the new stuff doesn't make, they make CMOS equipment. They don't make NMOS sensors. So this is actually a good thing in the long term, and I think that we're going to have high-performance cameras for many years to come. So, any questions?
Doug?
Yes.
For a comparably sized sensor, CCD versus CMOS, so physically comparable size and the number of pixels in that, is there a substantial difference in the temperature they run at?
Temperature. Well, the CMOS sensors have some actual active electronics in them, so they're going to generate a little heat. But the actual specifics of how low their dark current is depends on very detailed specifics about how this wafer is put together, how it's designed. So it's hard to really generalize. You know, like the Sony CCD sensors have a lot lower dark current, for example, than Kodak CCD sensors. But it just means you have to cool like 15 or 20 degrees more. So it's really just a matter of how expensive the rest of the camera is in terms of doing long exposures, how cold you have to make the chip. We routinely achieve 50 degree below ambient temperatures on most of our cameras, so it's not hard to do really good cooling as long as you have the mechanical parts.
That's two-stage cooling, though.
That's two-stage cooling, yeah. Yeah.
Thank you.
Okay, yes, John.
Doesn't Canon make their own CMOS chips?
They absolutely do, and you can't buy them. So yes, some of the big DSLR manufacturers have they probably don't actually make them themselves. They probably have licensed them from companies like Sony, but you cannot buy those chips. They're proprietary to Canon, and no one can get their mitts on them unless you buy a camera, take it apart, take the chip out, build it into a new camera, which has been done. But again, they're always color chips, so it's not ideal for astronomy. There's someone back there, yes.
How do they compare in terms of wavelength sensitivity?
Well, if it's a backside illuminated sensor, it really will be about the same because it's still silicon, and the detection phenomenon is the same. It has more to do with coatings and things than anything else at that point. So ultimately, they will have the same performance. Yes.
Doug, independently of the economic factor, has CCD technology simply reached the end of the line? Has it reached a technological brick wall, or could they be further developed?
Well,
In terms of improving performance.
yes. Well, they have. I mean, it's been an ongoing process for many years. CCDs have been undergoing continuous improvement. They're not going to improve the quantum efficiency because it's kind of hard to beat 97%. But you know, like another 3, big deal. However, there are these EM CCDs, which is a technology you will not be able to replicate in CMOS very easily. So basically, these electron multiplied CCDs are super sensitive, super low noise, and there's a new technology from onsemi where it's a dual mode chip, and it automatically switches on a pixel by pixel basis between a regular CCD and being an EM CCD, depending on how much light was present, and that preserves the durability of the hardware. So that's an amazing sensor. I'm interested to get my hands on one of those. Anybody else? Yes.
You mentioned you have a company here in Ottawa.
Yes.
What's your product line? Is it something of interest or what? Is it
We make astronomical CCD imaging cameras at the SPIG line.
okay, for how level or for?
We have everything from a $700 camera for guiding up to a $30,000 camera for research. And yeah, we're expanding the line too, so we have a very broad range. One of the most popular cameras is the STF 8300, and that's about $2,000, and it's a very capable little camera. Anybody else?
Yeah.
Yes.
What kind of technology do they use when they go into the infrared beyond the normal visual spectrum?
Yes.
CCD type of technology?
There are, well, CCDs can work out to a certain range, especially if you have certain types of coatings on the CCD that can extend the spectral range of the device. For really extreme spectra, there are different sorts of devices that use a different material. And they're similar in the way they work, but they use a different sensor material. That's getting fairly exoteric. You don't use that for just taking hobby pictures, because they get it's expensive. Yes?
You mentioned that one of the problems was the CCD chips or the CMOS chips are too small. Would it be worth like stitching a bunch of them together to make a bigger area, or is that?
Yeah, well, it's tricky because the device would have to be designed to be butted together, otherwise there'd be huge holes in your picture, right? There actually are buttable CCDs, they call them buttable CCDs, and the electronics are all in the end, and then the thing is rectangular and they're designed to butt together in multiple dimensions and make these huge arrays of CCDs. And so you talk about these, huge cameras with ridiculous millions of pixels, that's what those are. But right now, the technology to do that in CMOS doesn't exist because no one's built it. Okay, was there anybody else? Okay, well, thank you very much.
Okay, did you get all that? We're going to test you on it later. All right, so thank you, Doug. So we're going to go right into our observation reports. We're going to finish this beautifully. And first up, I believe, is Rick Wagner.
Kelly, can we get the room lights down and all this from the, these rooms down there? Oh, okay. Oh, I want to find my lid.
Okay, I have control. No, other way. Oh, lots of dots. I should mention, I was out observing. Isn't that amazing? In the first 6 weeks of the year, I was out twice. In the last 2 weeks, I was out 6 times. And I've realized what it is I'm wearing my astronomy socks. I'm going to go out and buy another 12 pair of those, and we're going to have lots of observing. So I have 2 comet pictures to start with. This is Honda Merkos Pajdusakova. I did this back in the middle of the month. This is about an 18 minutes exposure. I was trying to do an RGB color image, and for some reason all the R images had this, the top half of the field was all faded out or something. So it was, I'm not sure, I was getting some scattered light off of something. No, the chip's fine. So this is with a refractor, a 90 millimeter f4.5 refractor. This comet is good in position in the sky at the middle of the night. And the other one, where am I? Go. Okay, keep going. There we go. Comet 41P Tuttle Jacobini Kresak. It's the little fuzzy guy in the middle there. And this one's 34 minutes. I shot this one with my Canon 60DA on the same refractor, also on the 17th of February. And the reason, it's laser work here, there we are. It's pretty small. Actually, the comet is probably about that large if you get it on a really good screen. So it's small. what's really interesting about these two comets is they're actually doing research that amateurs can get involved in. The Planetary Science Institute has the 4P Coma Morphology campaign. And what they want you to do is they want you to take fairly detailed photographs of these, ideally tracking the comet rather than the stars. You can see oops, I'm always getting the wrong button here. In this picture, you see I'm tracking the stars, and the comet is moving quite rapidly across the stars. So then when I align all the pictures on the comet, all the stars end up trailing. So ideally, that's the way you should take the pictures. You should track the comet directly, and you get more detail in the coma. And so that group at the Planetary Science Institute and a Pro-Am Collaborative Astronomy project is also looking for amateur images of these two comets. So we can actually contribute to these projects, and if you take nice enough pictures, they will actually put you as a co-author on the paper. So something that's kind of interesting. And if you go and look up their websites, they do all kinds of other cool stuff too. So the next night I was out, I went down to the dock, and this I was using my barn door tracker, my Canon camera, and 18 millimeter lens, blah, blah, blah. 24 millimeters. I had it set at 24 millimeters. So this is actually 3 panels done down at the lakefront. You can see Kingston is down in the right corner there. That's the light glow. But this is basically a panorama of the Milky Way, the winter Milky Way. So you can see there's Sirius down there, M46 and 47, the little clusters. Some nebulosity that I don't know what it is. The Rosette Nebula, here's Orion with its belt, and M42, the Orion Nebula. You can actually see the Horsehead Nebula in there. Barnard's Loop. I can never remember this guy's number, but it's a great big diffuse nebula. Some really interesting dark nebulae that you don't really see in the winter sky because the Milky Way doesn't stand out quite as brightly. Gemini up here, M35, IC443 nebulosity here. Yeah, right there. And then Auriga up here with IC405 and the Messier clusters. So here's a more detailed shot of Orion. And this one is 22 minutes of exposures with a 50 millimeter lens. And again, this was just done on a barn door tracker, standing down on the dock. There's Barnard's Loop. I've been out trying. Barnard's Loop is actually one of the challenge objects in the Deep Sky Challenge list. And I was out one of the nights last week with an 80 millimeter refractor and a hydrogen beta filter. And actually all this section of Barnard's Loop was just like dead obvious. It was quite easy to see. So I've clocked that one. On the other hand, the Horsehead in here, even the nebulosity that it's forms its background, I couldn't see. So M42 in here is completely blown out. There's the big round guy at the top. You can see the color difference between Rigel and Betelgeuse. It's a nice area. So then I did a wide field shot from Auriga to Taurus. This one's just on the tripod, actually. 16 times 20 seconds exposures, so for about 5 1/3 minutes. And showing quite some interesting, oops, wrong button, always the wrong button. There's a lot of interesting stuff. The Pleiades, I was just reading, I think it's the latest Sky and Telescope talks about the Pleiades and how there's this cirrus that they integrated flux nebulae, and it's this very, very faint gas and dust and stuff that's just being illuminated by the starlight. So, but you can see that all through this area there's all kinds of dark nebulae that are quite interesting. There's the California Nebula. IC 405 Flaming Star Nebula here in Auriga. The Hyades, one of the open clusters in Taurus. So it's a nice area. So I was shooting on the tangential tracker, the barn door tracker, and it runs for about an hour and a half, and then runs out of screw threads and just kind of goes clunk, clunk, clunk. And I was running off operating my other two telescopes, and so this thing got accidentally left behind for about an hour and a half. And so what it does, though, of course, is that it tracks for about a minute and then clunks back. And so essentially these are like jiggly star trails. So I thought the effect was kind of neat anyway, with it all sort of sawtoothed. So that's 86 minutes of really bad tracking. So fortunately, before I got to the really bad tracking, I did actually manage to get almost an hour on Gemini. So there you can see Castor and Pollux up here, and then the legs of the two guys down here. There's IC 443 again, and 2174, and M31, or 35 rather, and NGC 2158, yeah. And again, dark nebulosity. And you can see the number of stars up here as opposed to down in the Milky Way. And I just did a quick close-up of M35, and it actually has the two little clusters. This guy is really spectacular. It's got so many stars in it, but it's very small, and I mean, it's actually a much better cluster than M35. It's just so far away. And finally, I get to IC 443 in between the 2 feet of Gemini, and it's got various names, but anyway, so it's kind of a nice nebulosity. So that one is, what are we talking here? 69 minutes, again with a Canon 60DA on the 90mm refractor. That's that. Thank you.
My first shot of a black hole. Sorry. Couldn't resist. Oh, there we go. Well, hi everybody. I thought I'd put together a few images tonight to show some winter objects. Obviously, great minds think alike, right, Rick? We're shooting in the same part of the sky. Has nothing to do with the fact that the sky has been basically overcast for the last 3 months. So, you know, we're shooting through probably the same sucker holes. But anyway, I did want to show you this because one of the things from our survey too is that I read just in the last couple of days, and thank you again for everybody that partook in that survey, is that people, especially people new to the club, are looking for, you know, even basic information like, you know, constellations, how to observe constellations and so forth. So I amended what I was originally going to show and threw in some wide field views that I actually just wound up taking in the last couple of days. And just to illustrate where some of the other images that I'll be showing, where they're located in the sky. So for those people that are new to astronomy or haven't done a lot of observing like the rest of us for the last little while, some of these targets that certainly that Rick showed and that I'll be showing are suitable for small telescopes and even binoculars there. So thought I'd just give you the overall view. This is obviously the view of winter constellations before we lose them for the season. Good old Orion there, pretty hard to mistake that one. We've got the Hyades up here in Taurus, and as Rick was showing, also a Gemini there. So this is, see if I can read my own notes here. Yeah, this is an 18-minute exposure, combined 18-minute exposure taken with a Canon 60DA and a 16mm lens. So very, very wide field of view there. You can see there's a bit of the red nebulosity from Barnard's Loop through there. And again, much more prominent in Rick's image there was the Milky Way. Certainly the Milky Way isn't as prominent as our summer Milky Way. And that's because we're essentially looking 180 degrees away from the center out towards the outer rim of our galaxy there. So yeah, it's certainly not as well populated with stars. So in terms of constellations, that's what you're looking at for those that aren't familiar. Good old Orion there, and you can see some of the major ones in here. I didn't toss in Monosaurus or any of the others that are sort of halfway in and out of the picture there, but certainly easy to recognize. And this is actually a really nice, rich area of the sky for binocular viewing and for small telescopes, because you've got an abundance of interesting objects in Orion, and certainly in through Gemini as well, all through this area really. And what I'm focusing on tonight is in that area there. So at the foot of Gemini, and Rick again showed you this. This is like the two of us came to the party wearing the same shirt type of thing. Anyway, it's not quite identical, but this is the area that I thought I'd zoom in on just to give you an idea of the kind of stuff that you can see. Obviously, these will be images, so they go a little bit deeper than you can see with a telescope, but certainly some of the objects like M35 are quite apparent even in small telescopes. So if we look at that, there we have a collection of really interesting objects in that very small field, and they're not associated with each other. They're at very different distances. They're very different types of objects. We've got M35 here, as Rick mentioned here. Rick also mentioned the Jellyfish Nebula up here, and down here we have the Monkey's Head, or the Monkey Head Nebula. So I'll have a quick look at each of these in a little bit more detail. That is, again, the Jellyfish Nebula, and this is a combination of broadband and hydrogen alpha imaging, a combined image of 43 minutes, taken with Canon 60DA. Sorry, Doug, that is a CMOS camera. Sorry. And yes, 37 minutes, and essentially this nebula is quite interesting. It's about 7,000 light years from us. It's a supernova remnant actually. It's estimated that the star that generated this structure exploded somewhere. There's a lot of uncertainty in the age, but the estimates range from between 3,000 to about 30,000 years ago that the actual supernova touched off, and that has expanded to about a 75 light year diameter. So it's quite a large object. Interestingly, though, too, this other part of this other nebulosity isn't actually related to the jellyfish. The jellyfish is actually superimposed on a much older supernova remnant, which is estimated to be about 100,000 years old. So yeah, it's become quite diffuse, but obviously still pieces of it here and there, and the jellyfish just happens to be siphoning in some of that, maybe just grabbing a snack. There you go. So that's the jellyfish. M35, as Rick mentioned, along with NGC 2158. These are both open star clusters, and they're interesting objects, certainly accessible with even small telescopes there. They are quite different in their distances. The estimated distance to M35 is about, if I recall, 2,800 light years. Whereas the NGC cluster is about 4 times further on. It's about 11,000 light years distant. It just happened to be sort of in a line like that. This is a quite a large structure. When you see this in the sky, this subtends a diameter very close to that of the full moon. So it's a large object. Oops, it's a large object. And contains about 200 stars in total. It's a combined mass within the sort of the central 10 light years of the structure, on the order of 25 to 3,500 solar masses. So there's a lot of mass packed into that into a relatively small space there. So that's M35, and the last one that I have for you is the Monkey Head. So So the Monkey Head is an H2 emission nebula. It's a rather interesting structure there as well. It's associated with, it's associated with the small cluster of stars here, and undoubtedly they are some of the primary sources of the energy being pumped into that, which is then later emitted by the gas in the nebula itself. The Monkey Head is quite large. It's let me see if I can read my notes here. Here we go. Should really bring my glasses there. It's actually quite large as well. It's about 75 light years in diameter. So in terms of its physical size, it's about twice the span of the Orion Nebula, but it's quite far away. It is about 5,000 light years distance, so very much more distant than the Orion Nebula.
Paul, can you point out the features of what makes the Monkey Head? Where the nose?
Sure. If you can see his mouth there, an eye socket, the nose there, the brow, right? And you'll notice the hair is very similar to my do tonight. I have been called a gorilla. Anyway, so that is the Monkey Head. Interestingly, if you were to take this image and rotate it 180 degrees, it also looks like a monkey's head, just in a different orientation, where this becomes the monkey's mouth, actually. And again, the eye socket's there, so depending on your orientation and how you're looking at things or photographing things. But this is the classical presentation of the monkey head itself. So, yes?
How do you know that?
How do I know that?
If you were to rotate 180 degrees.
Because I do that. I play with the images, and you know, it's like
You hang upside down from your.
hang upside down. Yeah, you've seen me do that in the observatory. And you know, I share a common thing with Brian there, because Brian sees all sorts of faces and things in the moon, right, Brian? Yep. Yeah, there you go. So, yeah, it's just kind of connecting the dots there. So this final image, all the other images that I shot were with the Canon 60DA, a DSLR. This is actually an image that I used two CCD cameras on. One was a one-shot color camera, and the other one was a monochrome camera based on the chip that actually Doug was talking about, the KAF 8300, which is a very nice chip there. So combined total exposure here of 45 minutes. And that's all I've got for you today. Thank you. Yes? Oh, thank you. See, I'm glad I told you that. I'm going to steal the stage just for a second, Oscar. Yes, thanks for reminding me, Janet. Some of you, probably most of you, know that Gordon Webster and Janet and myself are involved in arranging an exhibit of astronomical art as part of our GAA activities this summer. And that'll be at the Shankman Center. If you read your astronauts, you've already pretty familiar with the concept that we've been granted the opportunity to hang actually in the gallery there, in one of the galleries at the center, somewhere around 40 to 60 works of astronomically themed art. Now these aren't just photographs. These can be, you know, paintings. These can be fabric art. This can, you know, all manner of things. So it's a creative expression of astronomically themed art. So I just wanted to remind everybody here that what the process is essentially we've put out a general invitation to across the RASC, across all the various centers, for people to submit JPEG images of things that they would like us to consider for display in the gallery. So as it goes, essentially, once we have all our entries in, and by the way, the deadline for that, we just checked that, the deadline for that is March 31st to submit your JPEGs to us. We'll then collect the JPEGs. We don't know how many we'll get. We hope to get lots of them. We'll then sort through and set up a bit of judging on them to isolate it to the number that we've been granted to display there. So I just want to encourage everybody here
to submit your images or to submit your works of art. And I mean, don't feel intimidated or anything else. Art is art. It's a creative expression, and to say that one piece of art is better than another piece of art is bogus, right? It is a personal, emotional expression, and you see it in the images that are done by the various members. Everybody has a different approach. Everybody has a different style of processing. So it's all valid stuff. So feel free to submit. It doesn't cost anything to submit your images for our consideration. If one of your works is chosen for display in the gallery, you'll be on the hook for printing it and framing it, because it has to be framed. But the upside of that is that those images, your works, will also be for sale at the gallery if you so desire. So you can set a price on that. That will be labeled as part of the display, and so you may recoup your investment on framing and actually walk away with a bit of a profit and a bit of a swagger in your step to say, well, yes, I sold two of my images. So, yeah. Oh, and we do limit, as again from our work in the astronauts there, we do limit it to 2 submissions per person. So please feel free to send us in your entries. We're really looking forward to it. We've started to get entries in already, and we're hoping to get a lot more. And like I said, don't be intimidated if you've just started. If it's astronomically themed and it's your work, please feel free to send it in. Any questions, Martha? No, this is open to across the RASC. So it's open to all members, all members in good standing. Okay, any other questions on that at all? No? All right, thank you very much.
Alrighty, so I'm going to continue the theme of winter objects here. So I've got this wide field image of the Orion constellation. So the Orion constellation contains 2 of the 10 brightest stars in the sky. So that's Rigel and Betelgeuse there. In addition, it also contains the Horsehead Nebula complex here, which is IC 434, the Flame Nebula, which is NGC 2024. The Orion Nebula Complex, which are M42 and M43. We've got Barnard's Loop there. The Witchhead Nebula and M78. So this image is a combination of both RGB and H-alpha sub-exposures. So I've got about 42 minutes of RGB data at 800 ISO through a Canon 60DA. And 40 minutes of H-alpha data, about 40 minutes at 3200 ISO. And both of those were through a 50 millimeter Canon f1.8 lens. Yeah, that's it. Thank you.
All right, so we've got our usual finishing messages. We'd just like to give a quick reminder about Earth Hour. If you're interested, Saturday, March 25th, 8:30 to 9:30 p.m., we just turn off all our lights. I don't think we use electronics either. So if you're interested, that's a nice little initiative. Next, we have a very interesting opportunity. Adam Rees is a Nobel laureate. He is an American astrophysicist, and he's coming to give a talk in Ottawa on March 29th. I believe it takes place at U of O around 4 p.m. That's it. And so he won the Nobel Prize in 2011 for providing evidence that the expansion of the universe was accelerating. And so that's exactly what he's going to be talking about right here. So if that interests you, it's all on the U Ottawa website. And I believe Simon's going to speak to this.
This is just a quick reminder and a heads up of what's to come. You may be aware that there's a small group of us who put together what we call the Ottawa Astronomy Workshop Series. It's meant as an adjunct, an add-on, giving some context to a RASC observing initiative, which is called Understanding the Universe. And the object of the exercise in both the RASC observing list and in our series is to get people looking beyond simply checking off an object they've seen through their scope on a list, a little bit like stamp collecting, and getting them to think about what does it mean? And if I don't understand what it means, what do the scientists think it means? So what we've done up until now, we've done a few of these now. We've had a general introduction, we've had a talk on how do you actually read star maps and find your way around the sky. We've dealt with stellar evolution, and most recently we did two, one on the science of globular clusters and one on the science of spiral galaxies. And you can actually find copies of the PDF presentations, PowerPoint presentations on Jim Thompson's website, and you'll perhaps be able to find that by Googling karmalimbo.com and find that there. So what's coming up is we've got another workshop coming up. Can I go to the next slide, please? Thank you. The next one is Jim's going to be giving a talk essentially on the sun itself. And that's on Thursday, March the 30th at 7 p.m. And it's going to be held in the offices, the meeting room at Jim's place of work, and the address is here. So he has to have a heads up ahead of time to know who's coming. That doesn't mean you can't turn up at the last minute, but he has to draw up a list for security in his office environment of names of people, get you to sign in on a signing list. What he'd like you to do is to contact him at topjimmy@rogers.com, and we'll put out an announcement on the RASC Ottawa, what do we call it, members internet list. Trouble is, it doesn't always get to everybody, so we wanted to make this little presentation here. So topjimmy@rogers.com if you want to let Jim know that you'll be coming along. Thanks.
Great, thank you.
So like I mentioned earlier, Stan Mott Library, I don't really have to speak to this book. I think we all know it by now. So of course, Hidden Figures is the story of three black women who worked for NASA in the 1960s, who faced sexism and racism and still managed to send men into space. So back in January, Dave Chisholm gave a full book report on this. So if you're interested, you can go back on Ustream or on YouTube and find out more about the book. So of course, membership, a regular is $75, a youth membership is $45. I listed all the benefits earlier. Of course, membership benefits, the Loan Library, that's the site of the Fred Lossing Observatory, I believe. And of course, access the Stan Mott Library. Like I said, you also get these publications, Astronauts Online. I believe the journal is online too. You get Sky News every 2 months, and you have access to the Observer's Handbook. Club information. Unfortunately, Anne and Art are not here tonight. So, like every month, the meetings are webcast on Ustream at this address. I believe you can find the address online if you need it. So, audience 117, thank you. So thank you to all the speakers, thank you to all the organizers, and there you go. After the meeting, like every time, we're going to go to Gracie's, which is just down Aviation Parkway. Turn right on Ogilvie, you can't miss it. So there you go. Next meeting on April 7th, same time and place, 7:30 p.m. And if you have any ideas, any suggestions, anything, please rate me. So there you go. So thank you for joining us. Thank you to those of you who joined online. And I hope to see you at Gracie's, and I hope to see you next month.